Thank you very much, Professor Baldock, and I would like to acknowledge Professor Messel here today. I remember also, as a school child, I remember admiring all of those who were able to go to this international science school. It is the first of the major international science schools, I think. Others have been established since, but this one still serves as the real model for all of the others. So I am hoping today to make you enthusiastic over the next two lectures about what I'm doing. It's not the only thing that's happening in science, and in fact it might not be the most important thing that's happening in science, but it's a lot of fun and it's an enormous enterprise. So it's a real pleasure for me and a privilege for me to be able to say a few words. Of course, I'm very scared about the lion's den with all the questions at the end, but that we'll tackle when it all comes. Anyway, this first picture shows on the left corner the Atlas experiment at CERN. That's one of the two largest experiments ever built around a particle physics accelerator. The main picture, though, has nothing to do with accelerators. It's looking back using the infrared camera of the Hubble telescope into the far past. And you can see the green rings around there, which identify a number of young mini galaxies that were created somewhere before 1 billion years after the Big Bang. That's a long time ago, 13 billion years nearly, but a long time after the Big Bang. The astronomers are looking back in time. As particle physicists, we are interested in the period even further back. We're attacking it in a different way, and we're looking at around about 10 to the minus 11 seconds after the Big Bang. We have not very much idea, only hypotheses, of what happened before then, but we would like to push back that knowledge as far as possible. Of course, it's even a conjecture that we have anything to do with the Big Bang, but that the current model is that particle physics and cosmology are very closely related around about that time. So that's what I would like to talk about today and how we do it. So today, in the first lecture, I will talk about using particles as a microscope, because these large detectors around accelerators are really microscopes. And then I'll talk about what we think we know about fundamental particles and their interactions, and I will say what we think we don't know about this model of fundamental particles and their interactions. And then I will talk about the Large Hadron Collider, the history of colliders, why we think this is good, and where we are in this enormous enterprise involving thousands of physicists and engineers to look back in the past. Tomorrow I'll discuss the experiments and the first physics results at the Large Hadron Collider. But remember, please, this enormous synergy between those looking back and those trying to recreate the conditions that we think might exist back there. So I'll first talk in the first part about microscopes. Here we see a large bear entering a cave late at night. I'm sitting at my campfire and I have no idea what's at the door of the cave. So I throw a whole set of illuminated basketballs at the bear and they stick on his body. I don't really know who he is, so I'm going to get rid of those basketballs and throw tennis balls. Still I have no idea, and then I throw marbles and I see it's a bear. rather a friendly bear, but who's very intelligent. What's the message? The message is that you can use particles to probe a target object. And the smaller the particle, the better you can see it. That's what we do in particle physics. Not only small particles, but very, very fast particles, energetic particles. Now, these are particles. What you're used to in microscopes is light. And in fact, if you shine light through a grating, you get a diffraction pattern, and you can resolve the peaks of a diffraction pattern more easily if you, or smaller distance of the diffractive grating, if you reduce the wavelength of the light. Here you see a human hair under a microscope, and using a visible microscope, you can reach a minimum resolution of round about 0.1 microns. If we use X-rays, which have a wavelength, just like light, of 2 or 3 nanometers instead of half a micron, you can reach resolutions well less than 1 nanometer. And there you can see a difference in height between two parts of an object of around about half a nanometer. That's light. Now, of course, what I spoke of earlier were particles, and what I speak there is light. This will be one of the few equations that I use in this talk, but in fact, if we have light of wavelength lambda, in quantum mechanics, we have a duality between waves of light and particles of light. And the energy is given, of a particle is given by a number h, which is a fundamental constant of quantum mechanics, times the speed of light divided by the wavelength. This is the equation that Einstein used in 1905 for photoelectric effect. But there is another famous equation which is even more fundamental, which is P equals h on lambda, which is the momentum of an object. This one talks about light, but this one talks about particles with matter. Not only do we have duality between photons of light, that is particles, the gamma rays, and the wavelength, but we have a duality between matter particles and wavelengths. Here you see a 10 kilovolt scanning electron microscope identifying pollen. And you can see how good the resolution is. Now, I talk about 10 kilovolts there. Let me just give you a little definition. 1 electron volt is 1.6 times 10 to the minus 19 joules. So good. We want to use in particle physics numbers that are easy to remember. Electron volt is much easier to remember than 10 to the minus 19 joules. What is an electron volt? It's the energy gained by an electron as it crosses a potential difference of 1 volt. A photon of light that comes from the sun, that's green, around about 530 nanometers, has an energy of roughly 2.3 electron volts. Or if you want, 2.3 times 1.6 times 10 to the minus 19 joules. Let us use now electron volts as our unit of energy. Now, one of the first particle physics experiments was by Rutherford just 100 years ago. He did exactly what I did with the bear. He threw a ray of particles against an object. This one is a radioactive source with 5 million electron volt alpha particles, which are helium, into a gold foil. And he looked at what was scattered. He found, rather surprisingly, that most particles didn't even scatter. They passed straight through, but a few of them scattered at very large angles. And from that, he deduced that the atom was made up of a central nucleus surrounded by electrons. And here you see the case of a hydrogen atom, a proton surrounded by an electron. And I'll try and make that work. And it turns. And you can see that it can either be looked at as a particle or as a smudgy kind of wave around the proton. Sometime later, still early particle physics, a different set of people, Kendall et al., in 1967 did exactly the same experiment. The energies were a little bit higher, between 7 and 17 billion electron volts, and they were electrons that they hit against a hydrogen target which consists of protons. And what they found, what they should have found if the proton was a single object, was that the electrons would bend like this. What they found was that many electrons didn't bend and others hit something solid within the proton. Of course, there were a number of other experiments. I heard the word building on the shoulders of giants. And a giant preceding this was Hofstadter, who indicated that proton had size. But Kendall et al. Identified these objects, and that led to the discovery of quarks. And here you see, inside a proton, 2 up quarks and 1 down quark, which I will describe in a minute. And they are all connected by little strings which we call gluons. The size of these quarks is less than 10 to the minus 18 meters. Very, very small. This shows you just another drawing of the experiment. Now, why do we want an accelerator and why do we want a collider? For the accelerator, we want to go to higher and higher energies. P equals h on lambda. The smaller lambda, the larger momentum, the better we can penetrate inside objects. Another fundamental law in physics is the conservation of energy and momentum in an isolated system, and in the collision between 2 particles, energy and momentum is conserved. The energy of the collision is the same as the total energy after collision. There's just one difference. Energy here is total energy, which includes the equation E equals mc squared. That's the famous equation which you've all heard of from Einstein. That means energy total includes mass. And in fact, the converse, as you'll see in a little while, mass is just energy in a very isolated space. So here we have the possibility, by going to high energy, of either probing deep inside an object or creating many new particles after a collision. Now, we would like to go to the highest energy possible. Most of the historical experiments, like the experiment of Kendall et al. In 1967, threw a particle at an object, a brick wall or a hydrogen target. What we do with colliders is to throw one particle against another particle. This gives us extra energy because the total collision energy is twice the energy of each beam. Here, the energy equivalent is proportional to the square root of the beam energy. So we can get much higher collision energies by using colliders. I would now like to work on a little bit on the standard model that we know right now. Now, this is a whole new ball game here, and you won't understand this to begin with. I'm just wanting, with this slide, to introduce what I'm going to talk about in the next 3 or 4 slides. This is our standard model of particle physics. And it's very, very simple. It consists of quarks and it consists of leptons. You'll remember that the proton was made up of 2 U quarks and 1 D quark and surrounded by an electron. These quarks and leptons are called fermions. And fermions are particles which have spin. Now, spin is an intrinsic property of the particles which is related to the angular momentum of a system, which is another conserved quantity in particle physics. Just think of them as having a spin like a top, except it's much more difficult than that because these are fundamental particles and have very small size, maybe infinitely small. The other particles are bosons. Bosons have integral spin, and we call them gauge bosons for reasons which I'll mention in a moment. These are the Z and the W, the photon which you've heard about, and the gluon, which I showed you in a proton. These are related to the forces, the strong force, the weak force, electromagnetic force, and there is another force which is not included here and is not included in the standard model, which is called gravity, which I think we all know about. So that is the standard model, and everything else follows from it. There's just one thing that I didn't talk about, which is the thing that combines all this stuff together, which is the Higgs mass. So now I would like to go briefly through what we know about the standard model. Here you see what we have. We have in particle accelerators, we have atoms which consist of electrons which surround a nucleus. In the nucleus we have nucleons, which are either protons or neutrons, and within the protons or neutrons we have these quarks. And we bang all this together. That's quite a complicated situation to try to describe. What we've done over the past 40 years or so is to bang such particles together, usually up quarks and down quarks from protons and neutrons. Now, the experiments from that have discovered other quarks and leptons, and this now describes the standard model that we know. This slide is a little bit busy, but let us give a few definitions. We've found many new particles called hadrons. Hadrons are experimental particles, including the proton and the neutron, but also other particles, and they're sensitive to what we call the strong interactions. They consist of baryons and they consist of mesons. The proton is the lightest baryon and the neutron is the second lightest baryon. They have integral charge. They have a defined mass, and remember I told you mass is energy. They're also fermions. Mesons are things like, you may have heard of pions, which are produced in the atmosphere by cosmic rays, for example. And the lightest mesons are pi zeros, or pi plus, or pi minus. And the mesons are unstable, but they have a defined mass, and they have an integral spin. From these particles which were discovered, and hundreds of these particles with their own masses and their own spins, Gell-Mann and Zweig in 1964 proposed a classification which led to the quark hypothesis. At that time, it only included the up quark and the down quark. They proposed that the quarks were fundamental particles, that is, were indivisible, that they had either charge plus 2/3 for the up quark or minus 1/3 for the down quark. They had an associated anti-quark, which is identical to the quark except opposite charge. And they're sensitive to the strong, weak, and electromagnetic interactions. We now know from the experiments that there are 6 types of quark. The last quark was discovered at Fermilab near Chicago only in 1995. We do not know that the quarks are fundamental. We propose that they are. We only know from the LHC in the most recent experiments that it has a diameter of less than 10 to the minus 20 meters, which is less than what we knew before. Before we knew it was less than minus 10 to the minus 19 meters. The electrons surround the proton. They don't fall into the, surround the nucleus, They don't fall into the nucleus, and that is already astonishing. That is to do with quantum mechanics, but it also means that they are not sensitive to strong interactions. Like the quarks, they do have a defined mass, they do have a defined charge, which is integral, and in fact they consist of 2 types. There's the electron, and there are what are called neutrinos. They're observable, what's more. Quarks are not observable. And these are hypothesized also to be fundamental. We know to our best experimental knowledge that they're less than 10 to the minus 24 meters in diameter. What we see in nature is this. We don't see these in nature. I'm exaggerating a little bit. We see muons passing through us from the decay of particles produced by cosmic rays in the atmosphere. But they are not stable. Everything decays down to the electrons, and the neutrinos are a little bit of a special case. Next thing we worry about are the forces. Now, if you think of forces, they can be a strong force, or we can think of them in another way. We already thought of waves being the same as particles. In particle physics, we talk about the exchange of particles being responsible for the force. And this shows you a way to think of the particle exchange. If you have 2 bathers in boats separated and they throw a ball at each other, they will move farther and farther apart. And in fact, the exchange of the ball is responsible for that force which repels them. What we talk about in particle physics is demonstrated here by a Feynman diagram. In this case, for an electromagnetic interaction and an electron repulsion. Here you see an electron in time entering and leaving. And here you see another electron entering and leaving. There is an interaction, a repulsion. This has negative charge, this has negative charge. 2 negative charges repel. Now this is shown in particle physics as the exchange of a photon, which is the gauge boson of electromagnetic forces, interactions. We have 3 kinds of interactions in the standard model, each represented by their bosons. In electromagnetic interactions, which is electricity, atoms, light, chemistry, electronics, the gauge boson is the photon, and the coupling strength is defined by the electric charge, which you know from currents. For weak interactions, the bosons are the W and the Z. And these are responsible for things like neutron decay, beta radioactivity, and neutrino interactions, burning of the sun, and things like this. And their coupling is proportional to the weak charge. The weak interactions are much weaker than the electromagnetic interactions and is much shorter distance. And this is because the W and the Z have mass. Very, very heavy. And I'll come back to that in a few minutes. You can see here the decay of a neutron. There is a decay of a quark, a coupling of the W boson to a quark pair, up and down, and here to a lepton pair, electron and antineutrino. Finally, we have strong coupling, and this is much more complex. Here we have the gluons that I showed to you in the proton, binding the quarks together. In fact, they're so strong that in the quantum field theory that defines strong interactions, the gluons cannot separate and be alone in space. They have to be within a nucleon or another colorless particle. Now, the coupling here is called color, and quarks have three colors: red, blue, or green. And in fact, they're coupled by their gluons, which are either red anti-blue, red anti-green, etc. And there are a total of 8 gluons which bind the quarks together. So here you see a red quark coming up, a blue quark going out, and the transfer of a gluon. Each of these forces is defined by a theory, quantum field theory, which we call a gauge invariant field theory, and which has an associated gauge boson. This is a very specialized term, and I'll try to explain this in a minute. You see a word symmetry here, and we'll come to that in a moment. What it means is very much as you would have, for example, in 2 plates with a voltage on one side and a voltage on the other side. You can have a voltage of 20 volts on one plate and a voltage of 18 volts on the other plate. This will give you a potential difference of 2 volts. Or you can have 1 volt on one plate and minus 1 volt on the other plate, and that will give you 2 volt potential difference. The acceleration of an electron between those 2 plates will be the same whether it is in the one with the 20 volt upper potential or the 1 volt upper potential. That is due to gauge invariance. So, we'll come back to the Standard Model now and the Higgs. The problem with gauge theories is that in the Standard Model is they remain invariant, like I said, for the voltages, only if the gauge bosons have a mass of 0. That's true for strong interactions. It's true for the electromagnetic interactions. The photon has no mass. However, the W and the Z are very, very heavy, roughly 80 or 90 times, respectively, heavier than the mass of the proton. This is, within the Standard Model, this is postulated as being due to symmetry breaking while maintaining the gauge invariance. And this is the Higgs mechanism that is due to Peter Higgs, Brout, and Engelert. Here, in particle physics, symmetry means sameness. Here you can see a square full of arrows, and they're going in every direction. No matter where I look, the arrows are the same, like the universe. Everywhere I look, it's the same in the big picture. Now, here you can see they're all going in the one direction. They've been forced to go in one direction, and this is a broken symmetry. It could have been that the arrows pointed in another direction or another direction. We don't know which way it is pointing, but it is pointing in a given direction. If I now look at another example, this is a Mexican hat. If I see a ball on top, this is an energy distribution, for example, as a function of a variable, which happens to be associated to gauge invariance. If I see the ball on top, it is in an equilibrium, and everything around it is the same. The slightest nudge, and it will fall down, and it will achieve a stable equilibrium down here. We don't know which way it would fall down because it's in unstable equilibrium. It can go in any way. But once it is down here, its position is defined. And this is called a broken symmetry, and in fact this is exactly what the Higgs mechanism is. It defines a minimum energy level at a non-zero value of what we see here as a phase, but which is a variable for what we are worried about. This ascribes to the particle a mass, and this is the Higgs particle. Let me give you an example in another way. Imagine a crowd of people, and they're in a room, a cocktail party, they're moving in every direction, so it's like my arrows, sameness in all directions. Then somebody comes in, some pop singer, Lady Gaga or somebody, and everyone is very interested. They all go and cluster around her. And there you can see that there is a broken symmetry. Now she's gone, but they're all talking about her after she's left. And that's the Higgs particle analogy. Bit like having a spoon in a pot of honey. While Lady Gaga came through, she had to slow down. And that effectively gave her mass. Now in the vacuum, in quantum field theory, the vacuum is not empty. The vacuum is very busy, and virtual particle-antiparticle pairs are created out of the vacuum for a very small amount of time. That vacuum is full of Higgs particles, and in fact the quarks and leptons and W's and Z's collide with them, and the Higgs gives to those particles mass, which is proportional to the strength of coupling to the Higgs. In the standard model, all the Higgs parameters are known except the mass. The coupling is known to all of the other fundamental particles, but the mass is not known. The mechanism was used in the 1970s to predict the W and Z mass, and it's confirmed in the 1980s. However, it's only one of many possibilities, and very major problems remain avec that hypothesis, which I'll come to in a little while. But it's the best we have and the simplest way which we know about to give mass to the W and Z bosons. And this is imposed artificially on the standard model. So where do we go beyond the standard model now? There are many, many problems. First of all, here you can see our proton, you can see the quarks, you can see the gluons, and I've made it a little bit more complicated now because you can have virtual particle pairs being produced in the nucleon. But there are many questions that remain. First of all, I'll remind you that all the generations, the 3 generations, are unstable. Only the first generation is stable, with the possible exception of the neutrinos. Here, my first question, are these the elementary particles or not? Maybe they're composite. And what is the origin of their mass? Look here, these up and down quarks are very, very low mass, a few MeV, million electron volts. The muon is identical to the electron, except it's 100 times or 200 times heavier. The tau lepton is even heavier. The same goes for this hierarchy of the other quarks. It's astonishing. Via weak interactions, these other families decay into this first generation of quarks, which is the world we know. If you like, you can think of this as the electron volt regime. you can think of this as the mega electron volt regime, and this is the tera electron volt regime, and they always seek to find the lowest energy. So that is a real fundamental problem. We don't understand this. We don't understand why God chose to have these other generations. We don't even know whether there are more generations. This is as far as we've experimentally found so far. And we don't know whether they're fundamental or not. This is a question to be answered, maybe by the LHC. We've talked about the electromagnetic weak and strong forces. We haven't talked about the gravity, because gravity is incredibly weak. And nobody has found a satisfactory way of including it in the standard model until now. Lots of people are worrying about it and make various hypotheses, and we'll talk about that later, tomorrow. But it's not a done deal. We don't even know whether the proton is stable. What we would like to imagine is to have a unified description of the forces. This was first done for electricity and magnetism by Maxwell in the late 1800s. And then it was done in 1967 when Glashow, Weinberg, and Salam combined the weak force and the electromagnetic force into a unified theory. But we haven't managed to, we've managed now to have a satisfactory description of the strong force, but not a unified strong force with respect to the others, let alone gravity. And this is something very important. We have why matter and antimatter in the universe. When we started the universe, as I will show in a minute, we thought matter and antimatter were produced equally, but that's not the case today. What is dark matter, what is dark energy, and what are the dimensions of space-time? So these are all questions which I'll come to now. First of all, back to the start of the universe. This is the model of the Big Bang of the universe. It started from some small point or small space, nobody knows. It expanded, we believe, and at this point in time, all the forces were unified. After an inflationary period of incredible expansion, we had the elementary particles in some sort of plasma, and at a point here, we had the symmetry breaking of the weak force from the unified forces. And from that, we expanded. Now, at this point, we expect that quarks and antiquarks were made in pairs, if we believe particle physics interpretation of the early universe. We know today that largely matter exists. Maybe there are other parts of the universe which are inaccessible to us that are antimatter, but that's pure conjecture. We know that in our galaxy and in every galaxy that we know about, it is predominantly matter. By going back here, it was antimatter. So we don't know how this changed. We have a phenomenon in particle physics for weak interactions called charge conjugation parity violation. One more conservation law, one more symmetry, which is broken in weak interactions, and this might explain some of the asymmetry which exists. If in the early universe there was an excess of 1 part in a billion of matter over antimatter, this would go some way to explain this effect, but at present our observed CP violation in particle physics is too low. We would like to investigate that at the LHC. Second thing concerns dark matter. We have this standard model of particle physics, but starting from Zwicky as long ago as 1933, there was the observation that the rotational velocity of spiral galaxies would not work if we had only the visible matter observed in the galaxy. This is a telescope observation. And in fact, it needed to have at larger distances from the observed matter, it needed to have a more or less spherical distribution of some additional matter which interacts with gravity. It cannot be something which is within the standard model, because it certainly doesn't have any light, and we don't know what it is. By the way, this has been confirmed more recently by many other observational studies in astronomy, including what's called weak gravitational lensing. We know that only 4% of the universe is made up of the matter as we talk about in the standard model. Something like 23% has to be made up of this unknown matter, and then there's another 72% called dark energy, which increases the acceleration of the expansion of the universe. So there's this enormous unknown part of the universe which is unexplained by the standard model. By the way, not every galaxy needs to have dark matter, and some galaxies have much more dark matter than others. But most of the galaxies that are spiral, like the Milky Way, seem to need to have dark matter in a large region not associated to the spiral itself. One favored explanation of dark matter is the existence of supersymmetric particles that might be accessible at the LHC. And if this were the case, and if we make certain assumptions about the theories of what we call supersymmetry, and then we would have the lightest neutral supersymmetric particle, which would be rather heavy, not observable at an accelerator so far, which could be dark matter. By the way, there's not a shred of experimental evidence so far for supersymmetry, and existing searches are not successful, but it's still a very attractive theory. It's not the only theory to explain dark matter, but dark matter is an experimental fact. What is supersymmetry? Basically, it's a symmetry between fermions, that is the quarks and matter, and the bosons, which is the forces, the Z and the W, and the photons and the gluons, but beyond a given mass scale. If it was not beyond a given mass scale, then we would already have seen it, but we don't see it. So it's got to be heavy and accessible only via accelerators at higher and higher energy. And what it does is to associate with every quark a heavier supersymmetric quark. This should have a twiddle on it to show it's a supersymmetric quark with spin 0, an integral spin. And so that's a boson. This is a fermion. And for every gluon, for example, a gluino, which is one of these, with a half integral spin, and that's called a gluino. Here you can see it. You associate with each quark a heavier partner. This has a very attractive motivation because I told you that the Higgs was introduced rather artificially into the standard model, but it's more naturally, in a very complicated way, but more naturally introduced into supersymmetry, and in fact there is more than one Higgs. It would also solve very important problems of the standard model because the Higgs particle has quadratic divergences as you go to higher energies and higher masses in the standard model, which would push it to a very high mass, which would not work. And in this model, the divergences which occur in the quark sector are exactly cancelled by the divergences which would occur in the supersymmetric sector, provided they have very similar masses. As I said, this is not the only way, but this is a major motivation for searching for these particles at the LHC. Another thing that happens with the supersymmetric particles is that I told you that we would like to unify forces in the early universe, which is what we see here. We would like to have the unification of the forces right at the start of the universe. And as you can see here, as you go closer to the Big Bang, the different strengths of the coupling for the different interactions become very close together at a very high energy, which is inaccessible to all of our accelerators, but the theories of gauge theories do not predict that they all come together with just the standard model. So the supersymmetry model would provide one pointer towards unifying the forces. As well, as I said earlier, in some such SUSY models, the lightest, heavy, stable, neutral particle could easily be the dark matter. So now we're going to talk. I hope I've convinced you that that it's very important and very useful and very interesting to try to investigate all of these things and all of what's wrong with the standard model. We want to find a mechanism for the mass generation, which might be the Higgs. We want to search for a solution of the dark matter problem, and we want to make progress in understanding the laws of the early universe. And what we're going to do with that is make the highest energy Hadron Collider possible, and that is the largest microscope on the Earth is built by a lot of people. Now, how do we build a Hadron Collider? It's all very easy. There are just two equations. First of all, we have particles that go around in a circle. Particles can be accelerated in a straight line, and some accelerators are linear in a straight line. But you can imagine that if we turn particles in a circle, and if we accelerate them every time they go around, then that's much more economical than having a straight line to Mars and having them accelerated all that distance. Now, we turn them in circles with a magnetic field. We have what are called dipole magnets, which have a field between two iron cores here, and a particle which goes through it receives a force. For example, an electron or a proton receives a force which forces it to go in a circular orbit. So we build a ring and we surround it by magnetic dipoles. That's the first thing we do with a Hadron Collider. Now, as I said, we have to accelerate the particles. These don't accelerate the particles, they only turn it into a ring, into a circle. So at two places around the ring, we accelerate the particles. And this is called a radio frequency cavity. I'll show it to you in a minute. In addition, we want to focus the particles at various positions and have them to be collisions. And there we have quadrupole magnets, which is an example is shown here, which is just like a lens. It causes a defocusing or a focusing depending on the shape of the quadrupole field. So this is just two magnetic fields and one electric field, and you've got yourself a collider. Very, very simple. It's the last year of high school or the first year of university. The trouble is that this is not so simple. This is one of the amazing technological feats that all the engineers have developed over the last 30 or 40 years. Just one small point, as you increase the energy, of course, this force of the magnetic field makes the particle go into a larger and larger circle. You want to keep it in the same circle, or otherwise you'd be building bigger and bigger accelerators all the time. That wouldn't work. So you have to maintain them in that circular orbit, so the magnetic field has to increase as you increase the energies. Okay, so that's the principle of the field, of the collider, or the accelerator. I wanted to talk just 2 words about acceleration. F equals QE, that's the acceleration. A very simple formula, just the electron between 2 plates. That's the same as a skier going down a hill. It's called a DC accelerator. Bluff. Here is the surfer at Bondi. That's my niece there, I think. She is sitting on top of a wave, and she is being accelerated by the wave. And this is a punctual thing because the wave passes and she's finished. She is accelerated only for a limited period while she's on the crest of that wave. This is exactly an RF accelerator. This is a complicated slide, but I'm only wanting to show you what an RF cavity looks like. Here you see an example of one, which is a superconducting RF radio frequency cavity developed at DAISY in Germany for a linear collider which is being planned for the future. Here you have a magnetic field which produces an electric field. We won't go into the reasons of that, but there's an electric field produced in the vacuum tube in the direction of the particles. And the particles come in here, they're being accelerated here by the wave, and when they get to here, the wave has passed by and they get accelerated in this, all the way through that acceleration cavity. Now, there's one more thing which is important. If you have a wave that passes by and a particle is here, that's not going to be much good. It's going to miss the wave, like I do 99% of the time when I'm surfing at Bondi. I'll miss it. However, if I'm a good surfer, I will be sitting on the crest of the wave. Here you see the cavity. The guy A is in the right spot for being the surfer. B is a little bit behind. He's on the crest of the wave. And he will be accelerated faster because he's got a higher field. And so he will go in front of A, and the next time around he will be in front of A, so he'll slow down. So if we have bunches of particles in the machine, they will all ride the wave together. They will jiggle about around a central value, but they will stay in a bunch. And we need bunches in accelerators. So this has all been developed over the last many years, and in the early 1970s, the technology was sufficient to have colliders. There were 2 types. There were electron-positron colliders in green, and there are hadron colliders. First of all, what was called the intersecting storage rings at CERN in 1970. Then the proton-antiproton collider at CERN started in 1982. Then the Tevatron at Fermilab near Chicago, which started in 1987. And then the LHC, which started in 2009. They go to higher and higher energies. This is the average energy of the quarks in the proton or antiprotons. And this is the average energy, this is the exact energy for electrons and positrons because they're fundamental particles. So here you can see we've gone to higher and higher energies, and we've made major discoveries at each stage. Here we discovered the C-quark. Here we discovered the gluon. Here we discovered the electroweak model in a lot of studies at LEP. Here we discovered the top quark. And here we discovered, God knows, maybe the Higgs, maybe not. Now, the Hadron Collider is much, much more complicated than that little ring I showed you earlier. You start off with a hydrogen bottle, and you ionize the hydrogen in an electric field. Then that enters into a linear accelerator, which goes into this proton synchrotron booster, then the proton synchrotron, and then into a super proton synchrotron, increasing its energy at each stage, and then into the LHC. And in the LHC, it's injected at 450 giga electron volts, and it's accelerated finally in the future to 7 TeV, but today until 3.5 TeV. That is tera electron volts. Now, I'll show you what happens here. I hope I can. Go. Please go. Right. Here it enters the booster. It accelerates to 1.4 JeV. Here it enters the proton synchrotron. That's 50 years old, by the way. One builds accelerators one after the other. Now the SPS, up to 450 GeV. And now the LHC, and it's accelerating. It's up to 3.5 TeV. Now we stop in front of the mathematics describing the standard model. We cross the French-Swiss border 11,000 times a second. We jiggle around with the quarks as they go faster and faster. Now they're coming into the collision point. This happens to be the Atlas detector. And now you see two protons colliding. In fact, it's the quarks colliding. Wow! And now you see a lot of new particles. And that's what we will describe in detail tomorrow. Now, I'm going to give you another formula. N equals L sigma. Don't worry. It's not very difficult. Let's talk about sigma. Imagine a tiny particle, say an electron, hitting a billiard ball. Tuck. The size of that billiard ball, let's suppose it's a proton, which is, say, 2 times 10 to the minus 15 meters diameter. So then the cross-section will be the frontal surface of the billiard ball against the little electron as it hits. And that will be 10 to the minus 25 centimeters squared. Tiny. But it's a number, and it's just like 2 billiards on a billiard table, except we have a little puck and a big billiard ball. Now, 10 to the minus 25 centimeters squared is a very difficult number to deal with. We're going to deal with numbers that are easier to worry about. And we define one barn, and the original idea of a barn was a tennis ball hitting a barn. You know what a barn is, right? And that we define as 10 to the minus 24 centimeters squared. And here we have 10 to the minus 25, and that's 100 millibarns, or 1/10 of a barn. That's what we define as a cross-section. Now, the number of interactions times this happens will depend on the number of particles per second and per centimeter squared coming against the balls, and the number of billiard balls which are there to be hit per unit volume. And that defines the luminosity. The luminosity depends only on the machine. Sigma is the physical process, and NA for process A is what we measure, what we see. Now, what we're going to do now is talk about what we measure. This shows you the dependence on energy, collision energy, of cross-sections of various known processes and unknown processes. This second line here is 7 TeV. And you can see that the total cross-section for two protons hitting each other is around about 70 millibarns. That's that point. What we have here is the need to look at other processes. That is just the most common process, any interaction. We would like to look at the production of W and Z bosons, for example. Look how much lower it is. 1, 2, 3, 4, 5, 6, 7. 7 orders of magnitude. 10 million times less probable. So think of that just as a probability. And so we need to have a high value of L to see W and Z bosons. To do this, what do we need? We need, suppose we have a luminosity of 10 to the 33, which is 1/10 of the design luminosity of the LHC, and sigma of 1 nanobarn, process A will occur 1 time per second. And to do that, we need to have a lot of bunches in the machine. The design of the LHC is for 2808. We need to have the largest revolution frequency possible. The design is 11,000 rotations per second. We need to have a lot of bunches, a lot of protons in each bunch, 10 to the 11, 10 billion per second, in each bunch, I'm sorry. And we need to compress these bunches as much as possible because A squared is the frontal area of the bunches. And we need to keep that as low as possible. So we maximize N beam, NE, and minimize A. This is a tremendous technological feat, but it is very simple in principle. So the LHC is now sitting on the French-Swiss border. Here is Lake Geneva, and these are various towns around the lake. This is where I live, and this is 27 kilometers long. It is a machine that accelerates to 7 TeV, each beam, to a total energy of 14 TeV. Actually, it goes to 3.5 plus 3.5 TeV. It also has lead-lead collisions for 1 month a year at a design energy of 5.5 TeV per nucleon, and at present 2.75. It's a circular machine, 27 kilometers and 100 meters underground. And the collision frequency at each of the experiments is 40 megahertz. The energy per beam is 300 megajoule. That's the kinetic energy of an aircraft carrier going at 10 knots. However, it's associated to a beam which has a surface, a fractional area of a fraction of a square millimeter. So it's quite a lot of energy. And you have to not only create that energy, but also protect against it. 7 trillion volts on a proton, that's an enormous amount of energy. That's 500 kilovolts in air. And I'd hate to think how a lightning bolt would hit a proton. Now, this is another view of the LHC, and there are 7 experiments surrounding the machine, each of them 100 meters underground. This shows you the Atlas experiment. And 2 of the experiments are large and general purpose, and we'll mostly talk about those. They're called Atlas and CMS. There's also LHCb for B physics and CP violation, and Alice for studying in detail heavy ion collisions, and 3 other smaller experiments. Australia and New Zealand and India and Japan are involved in very large amount in all of these experiments. In particular, the Japanese have a very large contribution to Atlas. India has a very large contribution to CMS. Atlas has collaborators at Sydney, Melbourne, and in future Adelaide. CMS has collaborators in New Zealand, at Auckland, and Christchurch. So these show you the different experiments. So the ones we'll talk about are Atlas and CMS, and that shows you a closer-up view of the machine. This shows you the reality of the HF, of the radio frequency acceleration. You can see the RF cavity here. There are two bunches of those, two collections of those around the ring. And every time the particle goes around, it increases 16 MeV in energy. So it takes something like 20 minutes to accelerate the particles from 450 GeV to 3.5 TeV. These machines, these RF cavities operate at superconducting temperatures because of the currents that are needed to create the field that's required. And it's at minus 269 degrees centigrade, 4 degrees Kelvin. This shows you the magnets. These are the dipole magnets. Each of them is nearly 15 meters length, and there are 1,232 superconducting magnets. And to get the currents that are needed, 12,000 amps in each of these magnets, you need to have a field of 8.4 Tesla to keep it in the ring, and so you need superconducting technology. Just to show you, just to remind you, it's 8.4 Tesla, and the Earth's field is 3 Gauss. We also have 392 quadrupole focusing magnets around the machine and 4,500 other correction magnets around the machine. Just to show you how difficult this is technologically, the LHC ring shrinks by 15 meters in radius during cooldown. And so you have to keep all of the beam pipe in sync and all of the magnets properly collected during cooldown. And this is, by the way, what happened in a famous accident in 2008, which delayed the LHC by a year. So here you can see a photo of the magnets, the dipole magnets. The field goes up in this beam type, in this vacuum tube, and down in this vacuum tube. The protons are accelerated in each direction, one in this tube and one in this tube, bunches, and they collide at certain places around the ring where the experiments are. CERN has the world's largest refrigeration plant. It's one of the coldest places in the universe, with only 1.9 degrees Kelvin for most of the 27-kilometer distance around the ring underground. It's also the emptiest place in the solar system. We need to have a pressure inside the vacuum tubes where the beams go of something like 10 times less than that which is on the moon. It's also one of the fastest racetracks on the planet. Several thousand billion protons traveling at 99% of the speed of light will go around the ring 11,000 times a second, showing their passport at every turn of the Swiss-French border. And this is what happens. This is a reconstructed event within the Atlas experiment of a heavy ion collision. And you can see, remembering E equals mc squared, you can see all the particles produced. We're going to talk about that in a moment, in the next lecture. But just remember that the density of energy at that point is what we're talking about here, right at the start of the universe. This shows you another reconstruction of the event in Atlas. I'm nearly finished. I told you that the luminosity had to be as high as possible, so we increased the number of bunches, the intensity of the bunches, and so on. And this shows you how we've progressed. This shows you the first collisions in 2010 at 7 TeV collision energy. There were a few collisions in 2009 at a lower energy. And here is when the machine was starting to work. Here, the machine really started to work well. and we reached a peak luminosity of 2 times 10 to the 32 centimeters to the minus 2 per second in 2010. Don't worry about these units. Just look at the 10 to the 32, because the design luminosity for LHC is 10 to the 34. So we are, at the end of 2010, 100 times less intense than the design. That's all that matters. And then in 2011, we've been really going like crazy. Sorry, this is still 2010. We produced an integrated luminosity of 48.1 inverse picobarns in 2010. This is the period until the March 2011, but nothing happened after Christmas there. And this is, again, not the important number. It means simply relative to all the other numbers which we'll see in the future. Remember, 1 inverse picobarn means that there is a cross-section of 1 picobarn produced per second. Now, in 2011, we've managed, from a shaky start, things didn't go too well right at the beginning, and then they really got their act together. Amazing group of engineers, and these are shutdowns to make the machine better. And you can see that the peak luminosity has now reached to 1.3 times 10 to the 33, which is starting to be close to that, within shooting range of that of the design. And the integrated luminosity has been far better than we ever expected. The Director General gave 1 inverse femtobarn, that is 1,000 inverse picobarns, as the goal to reach in 2011 plus 2012. In 3 months, the engineers at CERN have managed to deliver this much to each of the ATLAS and CMS experiments, a factor 25 compared with what we received in 2010. We use this one, as you'll see next lecture, to reconfirm the physics we knew in the standard model. We now start to use this sample to search for the future. This is a busy, and I'm near the end, this is the busy table, and I don't want to go through the details. I just want to look at a couple of lines. We're only half the design energy, and this is because they have to shut down the machine and reconnect all the magnets very carefully over a period of a year in order to be able to safely reach 7 TeV. However, the transverse size of the beam is already better than the design, which is quite fabulous. The bunch intensity is already better than the design, which is fabulous. And the number of bunches in the machine is approaching half of the design. And this is because the bunch spacing so far is every 50 nanoseconds rather than every 25 nanoseconds. So you can only put 1,404 bunches in the machine. So we're nearly at the design level for 50 nanosecond operation. So they hope over the next months to increase the luminosity from 1.26 to roughly 5 times 10 to the 33, and to at 7 TeV to have luminosities well exceeding the design value. That would be great news. Now, this shows you the future. Hopefully, instead of 1 inverse femtobarn per experiment, we'll get something like between 5 to 15. Then we'll have a shutdown, and we'll go to 14 TeV, and we'll collect something like 100 to 200 femtobarns before a third shutdown, and roughly 400 inverse femtobarns after a final shutdown in 2020. Of course, this is very preliminary, but by 2030, they hope to collect 3,000 inverse femtobarns, 3,000 times the data that we have now. Of course, what happens here depends a lot on what we find in the coming months and couple of years. But who knows what this will be. There will be many of you, I hope, who will be, first of all, graduate students here, and then professors here, and then giving the lecture here when you're my age. Yeah. Finally, this shows you the Atlas experiment. This is a picture of one part of the Atlas experiment. It has 3,000 scientists from 174 institutes in 38 countries. This is the website if you're interested. And this is one of the two largest experiments. And in fact, this is the Australian participation. This is the CMS experiment. Has 3,600 scientists from 183 institutes in 38 countries. This is the website, and this is the New Zealand participation. We're going to talk about these next lecture. Let me conclude, and I'm a little bit late, 10 minutes late, I'm sorry. So we've introduced the formula showing wave and particle duality, and we've shown, I hope, how our accelerators are microscopes. We've introduced the standard model that works amazingly well at existing energies. We've generated mass with the Higgs mechanism, and we don't know whether this is the right mechanism or not. We would like to know. And we have many reasons to suppose that the standard model is only an approximation to something which is much more profound. And we want to search for these extensions to the standard model. We don't know how to yet. We have many ideas, and we have to explore that territory. The LHC and experiments may provide an answer to some of these questions, and to that end, I hope I've given you a flavor of how technologically challenging, but basically simple, the LHC is. And tomorrow, we'll talk about the experiments rather than the LHC and some of the early results and what might be expected in the coming years. Thank you, and I'll leave it.